Very good morning, students. Today we are discussing one new topic, that is P block elements. P block elements. In the previous section already we are discussing about P block elements, that is group 13 elements. Only retained syllabus we are discussing, only retained syllabus but not deleted syllabus. But in this session we are discussing both deleted and retained syllabus with competitive. Completely we are discussing P block elements. Completely we are discussing about P block elements. Therefore, while discussing the syllabus, which topics deleted, I will explain the topics you don't prepare for board point of view, whereas for competitive point of view you can prepare all the topics. Okay students, now in this P block elements, first syllabus we are discussing. After that, one by one topics we are discussing. The syllabus present in the P block elements are as follows. First one, weightage of this chapter will be 9 marks. The weightage of the P block elements is 9 marks. That is 2 1 mark questions, 2 marks question, 1 3 marks question. Students, total weightage will be 9 marks. Total weightage will be 9 marks. The syllabus of P block elements is like this. First topic, introduction about P block elements. Introduction about P block elements. Second topic, Boron family. Second topic, Boron family. Third topic, important trends and anomalous behavior of boron. Important trends and anomalous behavior of boron. Fourth topic, some important compounds of boron. Some important compounds of boron. Fifth topic, uses of boron, aluminum and their compounds. Uses of boron, aluminum and their compounds. Next topic, carbon family. Carbon family. Next topic, important trends and anomalous behavior of carbon. Important trends and anomalous behavior of carbon. Next topic, allotropic forms of carbon. Allotropic forms of carbon. Next topic, some important compounds of carbon and silicon. Some important compounds of carbon and silicon. These are the topics present, student. 9 topics are present in the first PU syllabus. In these 2 topics are deleted. That is 9th topic. Some important compounds of carbon and silicon is deleted, as well as some important compounds of boron is also deleted. Some important compounds of boron also deleted. Among the 9 topics, 2 topics are deleted. That is some important compounds of boron, 1 topic. Some important compounds of carbon and silicon, 2 topics are deleted. Okay student, 13 group 1 topic, 14 group 1 topic will be deleted. But in competitive point of view, if you want to attempt NEET as well as JEE examination, from these 2 topics also questions they will ask. That's why according to the given information from office, we are discussing total, board, competitive, all the syllabus. But while preparing board point of view, you neglect these 2 topics, that is some important compounds of boron in 13th group, some important compounds of carbon and silicon in a 14th topic. Okay student, right. This is about the syllabus and the weightage of this chapter. Next one student, first topic we are discussing introduction of P block elements. Introduction of P block elements. Okay student, in this introduction we are discussing what is P block elements. What is the P block element? First students, definition of P block elements: the elements in which the last electron enters into p orbital in their valency shell are known as P block elements. The elements in which the last electron enters into p orbital in their valency shell are known as P block elements. Next student, the elements which are present at the extreme right side of the periodic table. Generally, P block elements are present extreme right side of the periodic table. We know that. Observe the structure of periodic table. Extreme left side S block element, extreme right side P block element, middle of the periodic table D block element, bottom of the periodic table F block elements are present. The P block elements are present extreme right side of the periodic table. Extreme right side of the periodic table. Next student, the P block contains 6 groups. P block contains 6 groups because P subshell can accommodate maximum of 6 electrons only. P block contains 6 groups because the P subshell can accommodate maximum of 6 electrons only. If P subshell can accommodate 7 electrons, 7 groups are present. If P subshell can accommodate 10 electrons, 10 groups are present. In comparative point of view, they will ask student, how many groups are present in P block if P subshell can accommodate 10 electrons, 10 groups are present. 10 groups are present. Clear students? Copy this. Okay students, next continuation. The 6 groups present in the P block are as follows. The 6 groups present in the P blocks are as follows. In this we are discussing group number, group name and general valence shell electronic configuration of particular group. For example, group 13 P block contains 6 groups. They are group 13 to group 18. First one is group 13 Boron family. Group 13 are also known as Boron family because the elements present in this group are boron, aluminum, gallium, indium, thallium. Since the first element is boron, hence that is known as Boron family. And the general valence shell electronic configuration of these elements is ns2np1. Due to presence of 3 valence electrons in boron family, which is also known as third A group. This group number was given by Mendeleev. According to Mendeleev periodic table. Group 13 boron family. The elements are boron, aluminum, gallium, indium, thallium. General valence shell electronic configuration ns2np1, which is also known as third A. Remember student, this boron family is having 2 group numbers, that is group 13 according to long form of periodic table, group 3A according to the Mendeleev periodic table. Both group numbers you can remember. That is from long form periodic table, it is from Mendeleev's by using number of valence shell electrons. Where n is known as period number or valence shell number or principal quantum number. Where n is known as what student? Period number or valence shell number or a principal quantum number Similarly, other group students. Group 14 carbon family. The elements present in this are carbon, silicon, germanium, tin and lead. The general valence shell electronic configuration of these elements is ns2np2. Since 4 electrons are present, which is known as 4A. Group 15. The elements present in this group are nitrogen, phosphorus, arsenic, antimony, bismuth. Since the first element is nitrogen, which is known as nitrogen family, the general valence shell electronic configuration is ns2np3. Hence, it is known as 5th A group due to presence of 5 valence electron. This group, one special name is there, that is known as nicogens. Group 15 are also known as nicogens. Next, group 16. The elements present in this group are oxygen, sulfur, selenium, tellurium, polonium. Since oxygen is the first element, hence this group is known as oxygen family. The general valence shell electronic configuration of these elements is ns2np4. Hence it is known as 6th A group due to presence of 6 valence electrons, which is also known as 6th A group. These elements are also known as chalcogens. Next student. Group 17. The elements present in this group are chlorine, bromine, iodine, astatine. And these elements are also known as fluorine family because fluorine is the first element. These elements are also known as halogen family. The general valence shell electronic configuration is ns2np5, which is also known as 7th A due to presence of 7 valence electron. Similarly, group 18, which is also known as helium family because the first element of this group is helium. The elements present in this group are helium, neon, argon, krypton, xenon, radon. Since the first element is helium, these elements are also known as helium family. The general valence shell electronic configuration of group 18 elements is ns2np6. Due to presence of 8 valence electrons, this group is also known as 8th A group. These group 18 elements are also known as inert gases, noble gases, or red gases. First student, inert gases, because due to presence of 8 valence electrons in this cell, Generally, the elements which are having less than 8 electrons try to get stability by the loss of electrons, gain of electrons, sharing of electrons. Here, the group 8 elements already contains 8 electrons in its valence shell. There is no need loss, gain and sharing of electrons with other elements. Hence, these elements does not react with any other elements present in the periodic table. Hence, these group 8 elements are inert gases. Inert gases does not react with any other elements. They are inert in nature. These elements are also known as noble gases. Because even though they are inert in nature, after some years, due to very low ionization energy of xenon, they can react with fluorine and oxygen. They can form some compounds. Due to very low ionization energy of xenon, even though they are inert gases, they can form compounds with the highest electronegative elements like fluorine and oxygen. Those are xenon difluoride, xenon tetrafluoride, xenon hexafluoride, xenon trioxide, xenon tetroxide, xenon dioxidifluoride. These compounds are formed. How these compounds are formed? What are their preparations, properties, structures? In detail, we can discuss in your second PUC, P block elements, group 18 elements category. Right. In first PU point of view, at most they will ask question why group 18 elements are called inert gases or noble gases. What is the reason, student? Due to presence of 8 electrons in their valence shell, they are inert in nature. Due to low ionization energy of xenon, even though it is inert gases, they can form compounds with highest electronegative elements like fluorine and oxygen. Hence, these gases are known as noble gases. And these inert gases are also known as rare gases because they are present very less percent in the air. The percentage of abundance of inert gas in the air will be very rare, very less percentage. Due to this reason, these inert gases are also known as rare gases. One important point, student, in group 8 elements, all the elements are present in gaseous state. The only group in which all the elements are present in the gaseous state is inert gases only. No group does not contain all the elements in the gaseous state. In examination, they will ask student, which of the following group contains only gaseous elements? That is inert gases: helium, neon, argon, krypton, xenon and radon. Copy this, student. Okay, students. Next one, continuation we are discussing, that is the elements present in the same group are having same number of valence electrons but differ in their inertial electrons. Due to differ in their inertial electrons, the physical and chemical properties of elements of a particular group will be affected. Generally, students, the elements present in the same group are having same number of valence electrons but differ in their inertial electrons. Due to differ in their inertial electrons, the physical properties and the chemical properties of elements of the same group can be affected. For example, student, group 13 elements: boron, aluminium, gallium, indium, thallium. These elements are present. Boron atomic number is 5. General electronic configuration is 1s2, 2s2, 2p1. 1s2, 2s2, 2p1. Similarly, aluminium, Z is equal to 13. The general valence electron configuration is 1s2, 2s2, 2p6, 3s2, 3p1. Gallium, Z is equal to 31. The electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3p10, 4s2, 4p1. Observe these three elements electronic configuration, student. That is 2s2, 2p1, 3 valence electrons are present, student. And 2s2, 2p1, 3 valence electrons are present. 3s2, 3p1, 3 valence electrons are present. 4s2, 4p1, 3 valence electrons are present. Therefore, these three elements belongs to same group, hence they are having same number of valence electrons, but differ in their inertial electrons. For example, boron 1s2, 2 electrons are present in the inner shells. It is the valence shell, second shell. First shell is the inner shell, contains 2 elements. Aluminium, valence shell is third shell, but inner shell electrons are 6 plus 2 8, 8 plus 2 10. Here 2 inertial electrons, here 10 inertial electrons, 10 inertial electrons. Similarly, gallium 4s2 4p1, 3 valence electron, but inertial electrons are 10 plus 6, 16, 18, 20, 26, 28. 28 inertial electrons are present. 28 inertial electrons are present. Therefore, these elements are having same number of valence electrons but differ in their inertial electrons. Here 2, here 10, here 28 inertial electrons are present. Due to differ in their inertial electrons, the physical properties and chemical properties of elements are affected or modified or changes. The physical and chemical properties which can affected due to differ in their inertial electrons are as follows. Those physical and chemical properties are atomic radii, ionization energy, electron gain enthalpy, electronegativity, metallic and non-metallic character, and oxidation stage. These 6 properties we are discussing how they affected due to presence of inertial electrons. If you are going to student, rough diagram of the p block elements is as follows. Group 13, boron, aluminum, gallium, indium, thallium. Group 14, carbon, silicon, germanium, tin, lead. Group 15, hydrogen, phosphorus, oxygen, antimony, bismuth. Group 16, oxygen, sulfur, selenium, tellurium, polonium. Group 17, fluorine, chlorine, bromine, iodine, acetylene. Group 18, helium, neon, argon, krypton, xenon, and radon. These elements are present in p block elements. Okay, students. Now we are discussing these properties one by one. Okay, students. Copy this. Okay, students, next one. There are 6 properties we are discussing one by one. The first property, student, atomic radii. We know that in the periodic classification of elements, atomic radius definition. The distance between center of nucleus and the valence shell of an atom are known as atomic radius. For a group of elements, we can call it as atomic radii. Okay, students. Now we are discussing across the period and down the group of p block elements how the atomic radii changes. That is, across the period of p block elements down the group of the p block elements how the atomic radii varies. We are discussing, student, only gradation of these properties in p block elements only. We are not interfering S and D and F block elements. For these elements only, across a period of p block elements, down the group of p block elements, we are discussing. Okay, student. First one, atomic radii. Across a period, the atomic radii decreases because the electron is entering into same shell and effective nuclear charge increases. Because the electron is entering into same shell and the effective nuclear charge will be increased. Here, effective nuclear charge we are discussing, student. Why? Because it is more important for the further coming topics also. We are using this effective nuclear charge. We know the student, nuclear charge. The charge present in the nucleus of an atom are known as nuclear charge. For example, if the nucleus contains 1 proton plus 1 is a charge, 10 protons plus 10 is a charge. Nucleus contains protons and neutrons. Neutrons are chargeless particles. The charge of the nucleus only due to the protons only. Therefore, 10 protons are present plus 10. 1 proton is present plus 1 is the charge of the nucleus. That is nuclear charge. But effective nuclear charge means, with one example we are discussing, student, very clearly, very important, more concentrate. Let us consider these elements, that is second period elements in p block elements. That is, second period elements are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. But we are discussing about only p block elements. Boron, carbon, nitrogen, oxygen, and fluorine. Let us consider second period elements. The general electronic configuration is 1s2, 2s2, 2p1. For carbon, 1s2, 2s2, 2p2. Nitrogen, 1s2, 2s2, 2p3. Oxygen, 1s2, 2s2, 2p4. Fluorine, 1s2, 2s2, 2p5. Very clear, student. Here you can observe, as we go from boron to fluorine, as we go from boron to fluorine, the electron is enter into the same shell. That is the second shell. 1s2, 2s2, 2p1. The valence electron enter into second shell. Here second shell, here second shell. Across the period, the electron enter into the same shell. The shell number does not changes. That is, in the case of boron, 1s2, 2s2, 2p1, carbon 2p2, nitrogen 2p3, and oxygen 2p4, fluorine 2p5. Is there any change in shell number, student? The valency shell does not changes. Across a period, as we go from boron to fluorine, the electron is entered into the same shell. The electron is entered into the same shell. Here, if the electron is entered into the same shell, what happens, student? As the electron is entered into the same shell, effective nuclear charge will be increases. Effective nuclear charge will increase. For example, student, in the case of boron, atomic number is 5. Hence, 5 protons are present. That is, plus 5 protons is the nuclear charge. Here atomic number is 6, 6 protons is nuclear charge, 7 protons is nuclear charge, 8 protons is nuclear charge. Here 9 protons is the nuclear charge, 9 protons is the nuclear charge. Here the nuclear charge will be increases in the case of boron, carbon, nitrogen, oxygen, fluorine. Here in boron only 5 protons are present with the same distance, that is 2 shells. Whereas with the fluorine 9 protons are present with the same distance. Here, as we go from boron to fluorine, the number of protons increases, but distance between the nucleus and the valence shell will be same. Hence, here 5 protons can attract the 5 electrons with the same distance. Here, 9 protons can attract the 9 electrons. Here, the number of protons increases, nuclear charge increases. The nuclear charge is known as effective nuclear charge. Effective nuclear charge. The charge of the nucleus can affect the radius of the atom. Hence, that is known as effective nuclear charge. Effective nuclear charge. Once again, student, across the period from boron to fluorine, the number of protons increases, nuclear charge increases. Simultaneously, the electron is entered into same shell. Due to this reason, the nucleus of the atom can attract the electrons of the valence shell very strongly. Hence, what happens? In the case of fluorine, the valence shell is slightly shifted towards the nucleus. Hence, the atomic radii of the secondary period elements will be decreased. 9 protons can attract the nucleus, can attract the valence shell very strongly. Hence, the atomic radii will be shifted towards nucleus. Hence, the radius will be decreases. Clear, student? It is known as the effective nuclear charge. The charge of the nucleus nothing but number of protons. If the electron is entered into same shell, then the nuclear charge can affect the radius of the atom. Hence, that is known as effective nuclear charge. Repeat once again, student. Effective nuclear charge, more concentrate. Across a period, the atomic radii decreases because the electrons are entered into same shell. And the effective nuclear charge will be increases. If electron is entered into same shell, means distance between the nucleus and the valence shell will be same. But simultaneously, the nuclear charge will be increases. Here 5 protons are present. Here 9 protons are present. 9 protons can attract the electrons very strongly. In the case of fluorine, the valence shell slightly shifted towards nucleus. Hence, the atomic radius will be decreased. Therefore, the order of the atomic radii across the secondary period elements will be decreases from boron to the fluorine. Not only secondary period, student, in every period, the atomic radius will be decreases from boron to the fluorine. Because there is a student, effective nuclear charge will be increases. Okay. Next one, group. Down the group of the p block elements, the atomic radii will be increased because number of shells increases. And distance between the nucleus and the valence shell increases. Let us consider, student, in the case of 13 group, boron, aluminum, gallium, indium, thallium. Down the group, what happens, student? Number of shells increases. As the number of shells increases, distance between the nucleus and the valence shell increases. As the distance increases, the radius of the atom also increases. Let us consider, student, boron, 1s2, 3s2, 2p1, 2 shells are present. Aluminum, 1s2, 2s2, 2p6, 3s2, 3p1, 3 shells are present. Why? Because valence shell is third shell. Gallium, 1s2, 3s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p1. 4 shells are present. Previous we are discussing that example. Boron, aluminum, gallium. In these three elements, the number of shells increases. Boron contains 2 shells, aluminum contains 3 shells, and gallium contains 4 shells. The number of shells increases, distance between the nucleus and the valence shell will be increases. Let us consider, student, in the case of boron, 2 shells are present. In the case of aluminum, 3 shells are present. In the case of gallium, 4 shells are present. What happens, student? As the number of shells increases, distance between the nucleus and the valence shell increases, and atomic radius will be increases. Atomic radius will be increases. Okay, student. Next one. Second property, ionization energy. Ionization energy. Across the period, the ionization energy increases because effective nuclear charge increases. As the effective nuclear charge increases, the nucleus tightly attracts the valence shell towards itself. Hence, more energy is required to remove the electron. Hence, ionization energy will be increases. Ionization energy will be increases. Similarly, student, down the group, the ionization energy will be decreases because as the distance between the nucleus and the valence shell increases, then attraction will be decreases. Attraction decreases, the nucleus does not attract the valence electron very strongly. Hence, that electron can be removed very easily. Hence, the ionization enthalpy will be decreases. Ionization enthalpy will be decreases. Clear, student? More cautious. Ionization energy in periodic classification we are discussing. That's why we are not recall the definition. Ionization energy means the minimum amount of energy required to remove an electron from isolated neutral gaseous atom are known as ionization energy. Ionization energy. Okay, student. Right. Across the period, the ionization energy increases because the reason, student, effective nuclear charge increases. We know that across the period, effective nuclear charge increases. As the effective nuclear charge increases, attraction of the nucleus on the particular valence shell will be increased. Hence, the nucleus can attract the valence shell very strongly. Hence, to remove the electron from the valence shell, more energy is required. Therefore, ionization enthalpy will be increased. Whereas down the group, the ionization energy will be decreased because number of shells increases. Distance between the nucleus and the valence shell will be increases. Hence, less energy is required to remove an electron. Remember, student, here one equation I will give that will be very helpful to you. The ionization enthalpy always inversely proportional to the atomic radius. As the atomic radius decreases, ionization enthalpy increases. Atomic radius increases, ionization enthalpy decreases. Both are inversely proportional to each other. For example, in the period atomic radius decreases. In the period ionization enthalpy increases. In the group atomic radius increases. In the group ionization decreases. Both are inversely proportional to each other. Similarly, student, ionization is directly proportional to effective nuclear charge. As the effective nuclear charge increases, attraction of the nucleus on the valence shell increases. Hence, more energy is required. Therefore, ionization energy will be increased. Effective nuclear charge directly proportional to ionization enthalpy, and atomic size or atomic radius inversely proportional to the ionization enthalpy. Yes, students, in this one, from boron to fluorine, the atomic radius decreases. From boron to thallium, the atomic radius increases. From boron to fluorine, the ionization enthalpy increases. From boron to thallium, the ionization enthalpy decreases. Not only this group, student, every period and every group, the atomic and ionic radii as well as ionization enthalpy follows the following order. This effective nuclear charge more concentrated today. Copy this, student. Okay, next continuation, student. Next property, electron gain enthalpy. Electron gain enthalpy. EGE. We know that in periodic classification elements, electron gain enthalpy means the amount of energy liberated when an electron is added to isolated neutral gaseous atom are known as electron gain enthalpy. Now, across a period of p-block elements, electron gain enthalpy will be increases. Because effective nuclear charge increases. As the effective nuclear charge increases across a period, the nucleus strongly attracts the incoming electron, hence more amount of energy liberated, hence electron gain enthalpy values are increases. Down the group, electron gain enthalpy values are decreases. Because the distance between the nucleus and the valence shell increases. Down the group, number of shells increases. Distance between the nucleus and the valence shell increases. As distance increases, attraction decreases. The nucleus does not strongly attract the incoming electron. Hence, the ionization and thus, hence the electron gain enthalpy values are decreases. The electron gain enthalpy values are decreases. If attraction decreases, the nucleus does not attract the incoming electrons very strongly. Hence, the electron gain enthalpy values are decreases. Electron gain enthalpy values are decreases. Okay, students. Therefore, on conclusion, the electron gain enthalpy is inversely proportional to the atomic radius. Inversely proportional atomic radius. As atomic radius decreases, electron gain enthalpy increases. Inversely proportional to each other. Similarly, the electron gain enthalpy and effective nuclear charge directly proportional to each other. As effective nuclear charge increases, electron gain enthalpy also increases, because with the increase of the effective nuclear charge, attraction of the nucleus on the incoming electron also increases. Hence, the electron gain enthalpy values are increases. Next problem, student, electronegativity. Electronegativity. You can indicate with the symbol En. Simply can be called as En. Electronegativity. It can be defined as follows in periodic classification of elements. That is, the relative tendency of attracting of shared electron pair towards itself in a covalent molecule are known as electronegativity. The relative tendency of attracting of shared electron pair towards itself in a covalent bond are known as electronegativity. Across the period, the electronegativity values are increases because effective nuclear charge increases. We know the students, as the effective nuclear charge increases, attraction of the nucleus of the valence shell increases. Hence, what happens, student? The electronegativity will be increased. Electronegativity will be increased. With the increase of effective nuclear charge, the attraction of the nucleus on the valence shell increases. Hence, the atom easily attract the shared electron pair. Therefore, the electronegativity will be increased. Down the group, the electronegativity are decreases because the distance between the nucleus and the valence shell increases. As the distance between the nucleus and the valence shell increases, attraction decreases. Hence, the relative tendency of attracting of shared electron pair will be decreases. Hence, electron gain enthalpy values are hence electronegativity values are decreases. Here, student, electronegativity definition is important. The relative tendency of attracting of shared electron pair towards itself in a covalent molecule are known as electronegativity. Electronegativity means attracting of shared electron pair in a covalent bond. As the effective nuclear charge increases, attraction capacity increases, electronegativities are increases. Across the period ENC, effective nuclear charge increases, therefore electronegativity values also increases. Down the group, distance between the nucleus and the valence shell increases, hence attraction capacity will be decreases, hence the effective nuclear charge will be hence the electronegativity values are decreases. Down the group, the electronegativity values are decreases because the number of shells increases and distance between the nucleus and the valence shell increases. Therefore, attraction will be decreases. Hence, electronegativity values are decreases. An equation, student. The electronegativity is inversely proportional to atomic radius. As atomic radius decreases, electronegativity increases. As atomic radius increases, electronegativity will be decreased. Both are inversely proportional to each other. Similarly, the electronegativity is directly related to the effective nuclear charge. As effective nuclear charge increases, electronegativity values are decreased. Both are inversely proportional to each other. Okay, student. Next one, metallic and non-metallic nature of p block elements. The only block which can contains metals, non-metals, and semi-metals is p block elements only. S, D, and M block elements does not contain non-metals and semi-metals. Okay, student. Here, metallic and non-metallic nature of p block elements we are discussing. Generally, the elements can be converted into positive ion or cation by the loss of electrons are known as metallic nature. The metals can be converted into positive ion by the loss of electron. General equation is M gives rise to M plus N plus N electron. If one electron losses plus one charge, two electron losses plus two charge, an electron losses plus N charge. General equation for metallic nature. Here, the element which is having lowest ionization energy easily loses electron. Easily electron is removed. Hence converted into positive ion. Therefore, the metallic nature will be increased. The elements which are having low ionization energy easily loses electron can be converted into positive ion or cation. Hence, metallic character will be increased. Therefore, the metallic character is inversely proportional to the ionization energy. less ionization energy, more metallic character. More ionization energy, less metallic character. Both are inversely proportional to each other. Next, non-metals. The elements which can be converted into negative ions by the gain of electrons are known as a non-metallic character. If the element gets 1 electron, minus 1 charge, 3 electrons, minus 3 charge, an electron gains minus n each charge, because some elements get stability by the loss of electron as well as gain of electron. N plus n electron gives n minus n, that indicates general equation of the non-metallic character. General equation of the non-metallic character. Here the non-metallic character directly proportional to electron gain enthalpy, because electron gain enthalpy means the amount of energy liberated when an electron is added to isolated neutral gaseous atom, that is known as electron gain enthalpy. As the element is having more electron gain enthalpy, easily attract the incoming electron to form negative n. As the electron gain enthalpy of the element increases, electron attracting capacity will be increases. Hence, non-metallic character will be increased. Therefore, the non-metallic nature directly proportional to the electron gain enthalpy. Directly proportional to the electron gain enthalpy. Remember these two equations. Based on this two equation, across a period, the metallic nature decreases and non-metallic nature will be increases. Non-metallic nature will. We know that across a period, the ionization enthalpy increases. As ionization enthalpy increases, metallic nature decreases, because both are inversely proportional to each other. Similarly, down the group, metallic nature increases and non-metallic nature will be decreases. Why? Because down the group, ionization enthalpy decreases, hence metallic nature increases. Down the group, electron gain enthalpy values are decreases, hence non-metallic nature also decreases, because non-metallic nature directly proportional to electron gain enthalpy. Therefore, across a period, metallic nature decreases and non-metallic nature increases. Down the group, metallic nature increases and non-metallic nature decreases. Clear, student? Therefore, in the case of p-block elements, from left to right, the metallic nature decreases, metallic nature increases. From left to right, in the case of the p-block elements, left to right, non-metallic nature increases and non-metallic nature will be decreases. Non-metallic nature will be decreases. Hence, it is clear that the elements which are present extreme left side of the p-block can access the metals. The elements which are present extreme right side of the p-block elements can access the non-metals, because metallic nature decreases, non-metallic nature increases. More consistent. Across the period of the p-block elements, metallic character decreases. Decrease means highest to lowest, whereas non-metallic character increases, that is lowest to the highest. Therefore, the elements which are present extreme left side of the periodic table can access metals. The element which access extreme right side of the p-block element can access the non-metallic nature. Okay, students, like this p-block elements. Similarly, semi-metals or metalloids. The elements which are having both metals and non-metallic character are known as semi-metals or metalloids. Here, these elements are known as semi-metals or metalloids. Let us consider, student, in the p-block elements there are 7 semi-metals or metalloids are present. Those are boron, silicon, germanium, arsenic, antimony, tellurium and polonium. These elements can access metals as well as non-metals, that is semi-metals in nature. Left side of these elements metallic character, right side of these elements non-metallic character. Very, very important point. In the p-block elements, the elements extreme left side metallic nature, extreme right side non-metallic nature. In between these two, there are borderline elements. Those are known as semi-metals or metalloids. Those are 7 students: boron, silicon, germanium, arsenic, antimony, tellurium and polonium. Okay, students, these are the 7 semi-metals or metalloids. Semi-metals or metalloids. Copy this, student.